All right, welcome to another exciting episode of AP Chemistry here at Spain Park. Today is Tuesday, September the 9th. All right, so if you're enjoying these exciting AP Chemistry videos, please feel free to subscribe to this channel, hit that like button, and ring that notification bell. All right, here we go. So we're talking about why things are soluble in one another. So when we're looking at this is something that's super important, okay? This is how soap works, okay? We read about what does it mean to be hydrophilic and hydrophobic. Hydrophilic, water lover, waterphobic, water hater. In terms of polarity, hydrophobic is going to be non-polar, hydrophilic is going to be polar. So oils are non-polar. We know that oil and water pretty much don't mix. The non-polar oil and the polar water generally are insoluble in one another. So if you try to bathe without soap, it's not always going to work that well because the two don't like each other. The two are insoluble. The water's not that into the oil. That weak induced dipole attraction, nothing happens. So you have to have what's called an emulsifying agent. What was the definition of an emulsion? Okay, first off, am I supposed to have heard that? I saw your lips moving and I kind of heard something. You were right, something about a liquid, what?
It's like suspended in
A liquid suspended in another liquid. If you take Italian salad dressing and you shake it up, the oil and the water mix. It's an emulsion, but it's an unstable emulsion and it quickly separates back out. So you have to shake it up and pour it on your salad real fast before it separates back, okay? So we have to have an emulsifying agent, something that's going to link them together. So the oil on your skin and on your hair would be with water, it's an unstable emulsion. The two don't want to mix. And so we use soap, and soap is always going to be the sodium salt or the potassium salt of a fatty acid, which simply means that it's going to be a long hydrocarbon, non-polar portion, and then it's going to have a polar head. The fatty acid is going to be a carboxylic acid. That's what your C, that's a carbon, oxygen, oxygen, a COO. But the hydrogen has been taken off. It's been neutralized. So you have a fatty acid. You know, we can actually make soap from Crisco shortening. You can make soap. The original soaps were made from tallow. Does anybody know what tallow is?
beef fat.
Beef or sheep fat, or made from lard, which is pig fat. So original soap was always made from the fat. So when the butcher goes and gets all of the meat and they cut the fat all off, that fat would go to the soap factory. And they would make that. I actually have this box right here. This is how much of a nerd I am. I was at a nice fancy hotel, and I must have been, somebody else must have been paying because I never pay for a fancy hotel. It must have been at a conference or something. But I looked at this, and I looked at the box. Let's see if we can get to where it'll read. Darken it up, darken it up. Is that gonna make it worse or better? It's coming, right here. See, can you see what that says? Sodium tallowate. Now that is just a made-up word, but that simply means that this soap is a true soap, that it was made from tallow. Okay, so they get the animal fat, okay, and the animal fat is a fatty acid. It's got a carboxylic acid group in it. Then they treat it with lye, and I promise you this is the truth. Okay, they treat it with lye, L-Y-E. Okay, yeah, that was a dad joke. Okay, lye is a commercial name for sodium hydroxide. So they treat it with sodium hydroxide, and that neutralizes the acid. It pulls the hydrogen off, the tallow, the carboxylic acid, and it ends up giving us this carboxylic acid group right here, the COO, and then there'd be like an Na plus attached to it. Now the Na plus, when it goes into water, the Na plus just comes off. So we have this very polar end here. So the non-polar part goes and attracts to the non-polar oil. The polar portion does not go in, it stays out, and then the water is attracted to the polar part. It's an emulsifying agent. It links the two insoluble things together by having both a hydrophobic and a hydrophilic end. So as a result, it doesn't make the oil and the water soluble in one another. It just acts like a bridge linking the two together so it'll wash down the drain. Which is why it's important to use soap. Because otherwise, the oil and the water, your hair is just going to stay oily if you don't use shampoo of some kind. Your skin's going to stay oily if you just, use water. All soaps are going to use this basic principle. Now, the reality is most soaps nowadays are not made from tallow or lard. They're made from soybean oils, coconut oils, any type of oil that's going to have those fatty acids in it, and then they treat it. It's a lot cheaper to do that. And then they add moisturizers to it and all those different things. But the basic principle is still all going to be this. Technically, our soaps today are really called detergents. The difference between a soap and a detergent is soap is from natural, detergents are man-made. Most of our soaps are now all man-made, so they're technically detergents. And we call it laundry detergent, but we still use hand soap. But the hand soap is really a detergent because it's made from man-made stuff. It's not made from natural stuff as much anymore. It's not made from the tallow and the lard like this fancy soap was. Anyway, so that's the whole principle of an emulsifying agent. It links the two. It's got a polar part and a non-polar part. Links the two. Creamy Italian has egg whites added to it so that it doesn't separate. Mayonnaise has an emulsifying agent added to it so the oil and the vinegar don't separate. Okay, and it's those egg whites, which is why it'll spoil if you leave it out, out of the fridge. So a lot of things use an emulsifying agent to link the two immiscible, the two liquids that aren't really soluble in one another together. Now, the last part is even more important. If we look at this, what's the difference between a normal cell and a cell that's affected by, the sickle cell anemia? A normal cell is going to have what? Again, what's this group right here? That's your carboxyl group, your carbon, oxygen, oxygen, hydrogen. Whenever you have those oxygens in there, what's that make it, polar or non-polar? Polar. It's water soluble. So then it says, though, it goes to here, the abnormal cells, they're all just hydrocarbons. So what does that make them? Non-polar. But our blood is water-based, right? It's polar. So it says this change leads to the aggregation of the defective form of hemoglobin. What does that mean, the aggregation of the defective form?
Come together.
Say it again?
They come together.
They come together. Aggregation means they start clumping together because they're not soluble in the water any longer. And so they form big enough particles that the water can't stay suspended. So basically they're precipitating out. They're forming these particles that are then clogging the arteries and they collect in the joints, and it's extremely painful. Okay? It's a hereditary disease, and unfortunately, it's predominantly in the mainly African American male community. Now, they try to make a positive out of it, saying, yeah, but if you have sickle cell anemia, you're going to be much more, less susceptible. I'm trying to think of the word, but it's less susceptible to malaria. So you live in pain your whole life, but at least you're not going to die of malaria. And so it'd be great if somehow or other, a lot of times if it gets real bad, you got to have blood transfusions to try to get rid of the abnormal cells. And so it's really a very painful painful disease. But it's all based upon, again, the polarity and the solubility of the hemoglobin, and then the little bit of changes whether it's soluble or not, and changes the whole biochemistry going on. So this whole idea of like dissolving like and the polarity plays a big, huge part in vitamins, plays a big part in just medicine and the biology of life as is. I just think that this is pretty interesting, and just kind of seeing how everything that we're talking about kind of has practical applications. All right. So for the rest of the period, I want us, that is not what I want us to look at this worksheet, which is we did. We're missing page 2, and I was going to go run off some more page 2s. Somehow when it went through the printer, yeah, it's for a second. We're going to stop it here in a second. I'll run off the page 2 for you here in a second. Just for the record, I had to learn to copy or put 2 pages through at once. It wasn't my fault. So I want you to just kind of go through this. So I need 19 of these. Okay, this is all about IMFs, and I'm going to put page 2 up here until you get your own copy. This is page 2.